Okay, so now we have just done this state this theorem, that is theorem that states that you have a linear model and it tells you if a least square estimate exists, then it has to satisfy the normal equation. That's one thing that we'll try and show. But before we do this, I'll just try to give you an intuition of what the least square estimate is. We have done this before in the first class when we discussed linear models. So let's just recall a little bit. Just so this is lecture 2. So let's recall a little bit. I don't know if you remember this diagram we did the first day when we all came. So I said that you take n data points. There's something like this, and then you try to find the best line that fits them. And then one criteria we use for a line like this was we said, okay, we'll go here and everywhere we'll try and see how to sort of we'll try and take these perpendicular distances to a line, and then we'll try and see how to sort of this is what we did right long time back. And then so now one should let's say I make the distances like a little different color, let's say something maybe pink. So let's pink and let's go pink. So then you should go and see if I did this and how is this related to the linear model. Something you can try and do an exercise for this. So how is it related to the least square estimate? I'm sorry. Very good. So then this is what the LM function in R did. Right? And I also did I also told you how to do this, how to define a distance function and find the best line. This is day 1. This is from day 1, right? It's recall from day 1. So the exercises try to find a relationship for the least square estimate. Of valve with least square estimates. I think it's not that hard. I can easily check that this is exactly what the least square estimate is doing. It's minimizing it's taking all the perpendicular distances to the line and trying to find the best line that minimizes the distance. So it is able to find this beta hat that minimizes this quantity here. Very good. Okay, so now let me try and prove this theorem. The theorem will take some time to prove, but of course it's got a lot of linear algebra notation, and it falls out fairly easily, but one has to just keep track of the quantities carefully. Okay. So let me write the proof of theorem. So what's the first thing you do? So I want to minimize the quantity y minus x beta, right? So let me call that quantity R0. So we call the R0 squared. So instead of minimizing the quantity, I minimize the quantity squared. So same thing. So I minimize R0. I'll take the minimum or beta in Rm. Y minus x beta 2 whole square. I'll do this. Okay, this is all right. It's very simple. Then what I do is I'll show that R0 happens exactly at beta, where beta hat solves the normal equation. So we will show R0 squared is actually equal to y minus x beta hat, where beta hat solves the normal equation, which is x transpose x beta hat is equal to x transpose y. Very good. So that's what I'll do. Okay. So some crucial remarks. Let's do some remarks. Some crucial remarks. So this, even if you're not mathematically inclined, especially for applications, you must be careful that the beta hat is not unique. So solution set may not be unique. Okay, we only show it exists. Okay, just be aware of this. So sometimes when you write a solution exists, then it doesn't mean it's unique. So that's all the theorem is going to say. So now let's try and see how to solve. So let's try and see how to do this, right? Let's go step by step. So first of all, let's do a simple linear algebra fact. Okay. So suppose I know X transpose Y is a linear combination of the columns X transpose. So that's in the column space of X transpose. Right, that's easy to say. And the simple linear algebra exercise to show that, we'll come back to this in a second, maybe we'll try and recall some linear algebra facts, the same as X transpose X. Right. So once X transpose Y is in the column space of X transpose, which is the same as column space of X transpose X, then you have an immediate fact, right? This implies what? This implies there is a beta hat in Rm such that, so what is the column space X transpose X times beta hat should be equal to X transpose Y. Okay. So this is one fact that we can keep in mind. So if I show X transpose Y is in the column X transpose, that means there is some beta hat that gives it to you. So this equation has a solution always, because X transpose Y does belong to column X transpose. Right? So there'll always be one solution, but it may not be unique, but always be one solution. But now I have to show the least squared, the solution minimizes the R naught, the norms, these norms. This is what I have to show now. So existence is fairly easy. Now, how do I show it's unique? So let's go step by step. So now let's look at what am I trying to do. I'll take a beta in Rm. Sorry, I take a beta in Rm. Right. And what I do is I look at Y minus X beta squared. Okay, L2 norm squared. Okay, let's square that norm. So this is just so if you look at this, so recall before that if I take a Z in Rn, then the L2 norm Z whole squared is equal to the sum I equal to 1 to n of Zi squared. And that's what this is, right? So we'll make this small, take it here. Now this person right here, I will add and subtract a beta hat. Okay, so same as so we move this across here, take a beta in this, which is same as what I'll do is I'll add and subtract beta hat. So I'll X beta hat, which is what I want to compare. I want to show that's the smallest guy. And since I've added a subtract X beta hat, I'll add X beta hat. So I'll have an X beta hat minus X beta norm L2 squared. So I've done nothing, I've just added and subtracted a term right here. So I'll write a little jugglery. I'll write this as Y minus X beta hat plus X times beta hat minus beta norm L2 squared. This is what I'll do. Now I have two vectors, right? I have Y minus X beta that I'm interested in. I have an X times beta hat minus beta that I'm trying to gauge how large this can be, right? So now what I do is I do a little linear algebra trick. So now let's do a linear algebra trick. So here the trick is the following. So I take two vectors, let's say Z and W in Rn. So if you do norm Z2 squared, this is what? Summation I equal to 1 to n of zi plus wi the whole square. That's what it is, right? Now that's the same as summation I equal to 1 to n of zi squared plus summation I equal to 1 to n of wi squared plus I'll have 2 times summation I equal to 1 to n of zi and wi. That's what. But this I'll do a little trick. I'll write this as norm z squared plus norm wl2 squared, norm wl2 squared, and this one I'll write as an inner product of z coming out properly. Right. So where what happens where zw for any two vectors or any two matrices in fact is just going to be equal to z transpose times w. That's the inner product. So let me just rearrange this whole thing so that it's all clear. So I have this fact from linear algebra, right? This guy is there. So this fact is there. So we call this fact for any two vectors. This is a fact for any two vectors z and w in Rn. This fact we have, right? So what I'll use this fact on these two vectors. I'll take this vector y minus x beta as one vector and x beta hat minus beta as the next vector, right? As the two vectors that I take. So what will happen now? This is going to be equal to so the one vector z, this is the vector z that I have. So I'll call this as norm z squared from here, right? Sorry, from here, norm z squared. So it's norm of y minus x beta hat whole squared plus the second person is from here, right? That's w. So I have that. I have norm x beta hat minus beta norm 2 squared. I'll have plus twice the inner product, right? That's what I have. So what's the inner product now? The inner product of these two vectors, right? So twice the inner product of the vector y minus x beta hat and the vector x beta hat minus beta inner product. Right? This is what I have. Make it a little bit smaller so it fits in one line. Very nice. Very cool. So what have I done so far? All I've done, I just started off with the distance that I wanted to minimize. I took a vector bit. Then I plugged in my beta hat, which is a solution from this equation, right? This way. And the solution exists because x transpose y clearly a linear combination of columns of x transpose. So it's column x transpose space, which is same as column x transpose x, like a linear algebra exercise. And that means this is true. Very good. So that's what I got, right? So now I have this now. So now all I have to do is I have to understand, let me try to understand what this term looks like. Because this term anyway, if beta is equal to beta hat, it's it's 0. We have to understand what happens to this term. If this term is non-negative, then I'm done, because then I know my things. Okay, let's see. So now let's understand this term. Let's understand this term right here. How big can this be? The 2 for the time being. I don't need the 2, but let's understand how this term is. Okay, so what's that going to be? So that's going to be equal to, let's go back here, let's paste it again. Let me remove the 2. So it's going to be what? X transpose y. What is X? What's Z transpose w? Z is w, Z is y minus x beta hat. The whole thing transpose, right? And the other guy is x times beta hat minus beta. It's a scalar, right? It's a scalar. So some number like this. So if it's a scalar, I can take its transpose and it'll be the same thing. So that's the same as if I take the transpose of the transpose times x transpose times y minus x beta hat. So what I do here, I did the following. Since scalar, one can take transpose. So one can take transpose since it's a scalar. So one can take transpose since it's a scalar. Very good. So I'll leave this in. I'll just leave it like a box. Very good. So once I did that, now I go back to the equation right here. It's kind of funky. So I write this as, right? So I have beta hat, and then what is beta hat now? Y minus x beta hat, beta hat minus beta transpose this, right? So now I'll write this as beta hat minus beta transpose, right? I'll multiply the x transpose out. I'll have x transpose y minus x transpose x times beta hat, right? But what did I get here? If you look at this guy, that's the same as this person right here. If I go back up, this is exactly this. Let me make this into a pink one. This is how I chose a beta hat. So this is x transpose x beta is x transpose y. And that's exactly what I have here. X transpose y minus x transpose x beta. Right? So it's going to be equal to 0. So this is by construction of beta hat, right? Or say I'll just say choice of beta hat. Very cool. So it means now what happened in my least square estimate, this person is 0 now, right? So all I'm left with is now, so therefore, let me call this equation 2 or equation, let's say equation plus, let's say. So from plus, what have I shown? I've shown y minus x beta L2 squared is equal to just these two people, right? Let's call this plus and let's call this plus plus. So plus and plus plus. What have we shown? We have shown y minus x beta is just these two people. But alas, the second guy is non-negative always. It's a square, right? So it's a square. This person is always non-negative. So I gotta throw it away. So it's going to be bigger than equal to. So one thing, this is going to be bigger than equal to this person right here. Y minus x beta hat to square. That's simple. But moreover, what happens? And further, is equal to y minus x beta hat. When does it happen? It happens if and only if this term is 0. But this term is 0 when what happens? This is 0. That means beta hat is equal to beta. Cool. So therefore we have shown, if you cross all the t's, we have shown r naught squared is norm of y minus x beta hat norm 2 squared. Quite cool. That's the end of the proof. Right. So let me just go back and let me make a double thing and structure. So I was trying to prove this theorem, right? That I was trying to prove the fact that if you have a linear model, the least squared estimate is the one that solves equation 1, which is a normal equation. So I was trying to prove that. So what I do first? I said, let me come back here, let me keep this here. I said, first look at this. This is what I want to understand, this quantity, right? So I will show to you that R naught actually is equal to x naught minus this, where beta hat solves this equation. Of course, now I have to show a solution to the equation exists. It may or may not exist, right? So what I said was that you look at x transpose y. That's in the element of column space of x transpose. And that linear algebra fact, that's same as column x transpose x. That means there is one beta hat for which x transpose x beta hat is equal to x transpose y. Right? That's just the linear algebra fact, right? Very good. Now then I come down here. So I come down here, look at this equation right here, and I say, okay, fine. I look at y minus x beta for some beta, right? Then I see that I add and subtract a beta hat, x beta hat. Then I look at this as two vectors, y minus x beta and x beta hat minus beta. So then I use a simple linear algebra fact that if I take two vectors in Rn, the L2 norm squared is the L2 norm of each of these guys plus twice the inner product. So I do the same thing. I take this one vector, I take the next vector, I do L2 norm squared plus of the first guy, second guy, twice the inner product. Right? Once I do this, I say, okay, let's try and understand this person right here. So if I do the expansion of this is just transpose times the vector, this is what I have. It's a scalar, so I can take a transpose of that guy, that becomes this transpose times this. And what I do is I leave the first person as it is, and the x transpose I take inside. So I get x transpose y minus x transpose x beta. And lo and behold, that just matches exactly how I picked my beta hat. Right? So it becomes 0. So now you're almost there, because now you know that from plus and plus plus, that is from this equation and this equation, you know that L2 norm squared for any beta in Rm is going to be equal to the least square estimate plus this extra factor here. If you observe this guy is always non-negative. That means this person right here is always bigger than y minus x beta hat squared, L2 norm squared. And when is it equal? It's equal only if this guy is 0, and the guy is 0 if only beta hat is equal to beta. That means you have shown your R0 that you start off with is exactly y minus x beta hat squared. Quite cool. Nice. So I've shown you the existence of a least square estimate, and it solves the normal equations.